You can, it's going, you can, or you will, you'll be going to, well, the spreadsheet just to take a look at things. Today is the 15th. We're gonna do lesson 8. There's no worksheet associated with it. It's just the activity. Let's put it here. Okay, so it's just the bubbles on code. So let's take a look at them. For lesson 8, we are learning about color images now. We did black and white images before, and that is due to, what is that? Today, I suppose. Technically means at midnight, but that means I'll grade it sometime after today. And late, I'm going to put in whatever you have, 50%, 0%. And if you finish it after I put a 0 or 50% or something in, let me know that you finished it. Email me, put P3 in the subject line or sign it, your name, P3, and tell me the name of the assignment that you need reassessed. And so there's that. The color images, it's the basic idea for black and white image was each pixel had a single bit. And that bit was either a 1 or a 0, meaning either on or off. I can't remember if I showed you in this class, if I did or not. And I don't need to know, show you a picture, but you can all imagine what the power button looks like on everything. A power button is a 1 and a 0. That's what this symbol means, as in on or off. And the 1 and 0 being on and off in binary, it's the same thing, not just in images. It's a way of thinking about the way bits are actually transmitted. A small amount of electricity, like half a volt or something, through the processor or through the memory means on, and it means 1, and a lack of that electricity or voltage means 0 or off, and that's what that means. So as we build on our knowledge, we can now extend that to color images. And the idea for color images is that if you have 3 bits, at least 3 bits for each pixel, you can make colors. The computer will interpret the first bit for that pixel. Well, first of all, you'd have to, the computer, the sender and receiver, sender and receiving computers would need to, can you finish that later? Just go ahead and turn off your screens. Learn this now. Screen off. Awesome, thank you. The sending and receiving computer would agree upon a protocol. There would be metadata to describe how many bits per pixel. And so the receiving device would know every third pixel is, every third bit is a new pixel, assuming it's 3-bit color, which nothing uses 3-bit color. But it knows that of each 3-bit chunk, the first bit will always refer to the redness, okay? The second bit will always refer to the green, and the third bit will always refer to blue. It's always going to be in that order, red, green, blue. We obviously will get more bits per pixel later, allows more shades of color. But for this simple example, instead of just having 1 bit per pixel where each bit was either on or off, only gave you black or white, now we can have, it's essentially like having 3 different light bulbs, and you can either turn on just the red, just the green, or just the blue for the most basic version of each of those 3 colors. You could turn on the red and the green. We'll see what that does. You can turn on the red and the blue. See what that does. You could turn on the green and the blue. We'll see what that does. You could turn on all 3 of them, or you could leave all 3 of them off. And your options, if you think about 3 bits of binary, you can count from 0 to 7. 3 zeros in a row in binary is equal to 0. And 111 in binary is a 4 plus a 2 plus a 1 is 7. So you have 8 options when you have 3 bits. There's 8 different colors you can make. We'll talk about that here. So there's a brief video that will explain, for the most part, how the widget works, and we're going to watch it in a different window. If you're watching this asynchronously, I recommend finding the video and not watching it through the meeting that's being recorded now, but you know, you can, it's not that terrible.
In this version of the widget, we've made setting the metadata of the image a bit easier. For the width and height, you can type the decimal numbers you want, use the sliders, or type the binary as you did before. It's useful to be able to change these things quickly to see the effects on the image. Notice when you change the data by typing or using sliders, the binary data changes and the image canvas reflects the changes. There's another piece of metadata here called bits per pixel, which will allow us to make more than purely black and white images as we did before. To see what it does, let's set bits per pixel to 1, which is what we had for black and white images before. And let's paste in a familiar black and white image. In order for a pixel to have a range of colors, it seems logical that we will need several or many bits to represent the color of each pixel. The bits per pixel setting in the metadata tells the widget how many bits it should use to calculate the color of a pixel. You can see if I change the bits per pixel setting, the widget will interpret the bits differently, and you'll see some colors start to appear. Of course, the binary data for this image was written for a black and white image with 1 bit per pixel. But if we change how that data is interpreted by increasing the bits per pixel that the widget is expecting to see, the image gets garbled. Let's start over and try to get the hang of using color in digital images. I'm going to make a very small image so that we can really look at what's happening with the pixels. So I'm going to set the width to 4 and height to 2. Now let's look at how RGB colors work with this tool. As you know, for color images, each pixel is actually a combination of red, green, and blue light. If we want to represent that in binary, the least we can do is allocate 3 bits for each pixel, 1 bit each for the red, green, and blue values. I can use the slider to set the number of bits per pixel I want to use to render the image. So I'm going to set the bits per pixel to 3. So now, with 3 bits per pixel set, it means I can control the amount of red, green, and blue light that goes into each pixel. As before, if I turn all the lights off, I will get the color black. And if I turn all the lights on, I get white. Since I have 1 bit of control for each of the red, green, or blue lights, I can turn them on and off individually. So if I want a red pixel, I can turn on the red light and turn the green and blue lights off. So that's red on, green off, and blue off. 1, 0, 0. And presto, I get a red pixel. Now you keep going and create a green and a blue pixel. Notice that when we have 3 bits per pixel, the first bit controls the red light, the second controls the green light, and the third controls the blue light, R, G, B. Now it gets interesting. What happens if we mix the lights? Let's see what happens if we turn on the red light and blue light and leave the green light off on the same pixel. Before I type it, make a mental prediction. What color do you think we'll get if we mix red and blue? Think about it for a second. All right, ready? Here we go. Red on, green off, blue on. It made pink. Is that what you were predicting? I'm guessing that you thought we might get purple. Well, this is one of the key differences between mixing light and mixing paint. It's actually the opposite physical process.
So this is actually a better example of a concept of color correction, where you could record something, either screen capture or a video camera, and it will do its best to figure out what color something should be and put that into the memory. And it's not always going to be exact. It's sort of more of a magenta, and it's actually brighter on my computer than, you know, there's always darkness and red, blue color, you know, color warmth and balance on every display, no matter what it is, and it's always interpreted. And so, I don't know, I guess it's probably magenta technically, but yeah, that's red and blue.
When you mix a lot of paint together, the color gets darker and darker. When you mix a lot of light together, the color gets brighter and brighter. It can take some getting used to, but you'll get the hang of it. With only 3 bits, we know that I can only combine them 8 different ways. So with 3 bits, only 8 colors are possible. Now you keep going and finish the remaining 2 colors.
She kind of did there. Okay, so listen up and pay attention. We're going to go through this starting from bubble. What's bubble 3? Bubble 3 isn't the widget. Oh, hold on a second, clickers. So this is about 2 bits per color, and I don't know why they give that to you before we start talking about 1 bit. Like, just hang off for now. You're going to have plenty of time. Lev, awesome. Is that what we need to do? Which one is the first? Oh, no, here we go. Bubble 2 is the first widget, I suppose. And the goal here is to do that, but we need to come up with all 8 possibilities of 1 bit per pixel. Now, here's the thing. Let's go copy this. First, some things to notice. Let's go like this and go like this. And so you can see here, let's go readable like that. This obviously is a picture of nothing, but you can see when we put readable, we have 3 bits per pixel, and we're getting color. As we change the number of bits per pixel, we're only going to get any sort of color at certain intervals. Okay, we get it at 6, we get it at 9, we get it at 12 bits per pixel. Okay, that's 4 bits for red, 4 bits for green, and 4 bits for blue. And I'm guessing you've realized that we only get colors when we have a multiple of 3. Anytime we have less than 3, the computer has to interpret this long number as a % of gray. But that's fine. We're going to start with 3 bits per pixel. And our first goal is just a all 8 possibilities with 3 bits per pixel. And let's just do 4 by 2. And we'll delete all of the before we give the answers. Okay, and it doesn't matter the order, but you are going to do this in a second. You're going to do it on your computer. And when you're done, you're going to hit finish, continue next step, so that it saves on your account. And when I check to see that you've done it and done it correctly, it will still be there. Okay, so we have 3 bits per pixel. We already know we can do 0 is all black, and all 1s is white, but it's not like this is the number 7. We've done that before when we were converting binary to decimal. If you had 3 1s in a row, or even 6 bits and the last 3 are 1s, this would convert to 7, but it's not 7. It's 1 out of 1 for red, 1 out of 1 for green, and 1 out of 1 for blue. Okay, so this is just a different way of using bits. It's not, this whole number is not a single binary number. Okay, that'll make more sense later. So then we have the option of turning on only 1 of the 3 colors. Let's turn on just red. So that's red on, green off, blue off. Just green is only green gets the on light, and blue goes like that. Okay, then after that we can any combination of two. The first two on, the first and third on, and the second and third on. Okay, and those are the 8 colors you can make with a single bit per color, which is 3 bits per pixel. Okay, after that, you're going to go and we'll learn about 2 bits per pixel. 2 bits meaning for each of the bits, each of the pixels, you get a total of 6 bits to work with, and that's 2 bits for red. The 2 bits for each color are binary relevant or decimal relevant. I don't know what you call it, but it does go from 0 to 3, this being 3, in the amount of red, and you could do the same thing for each color and each combination of colors. So let's see if I've already done this. Yeah, okay, so there you go, you know where we're going, and we can always start over. So starting with a 4x3 canvas with 6 bits per pixel, again, that means 2 bits for red, 2 for green, and 2 for blue for every pixel. We're going to do the full shade of all 3 colors that you can do with this many bits. So for green, the lowest one that you can do is 0 red, 0 green, 0 blue. Okay, then we're still going to do, we're working our way up green. So we'll have 0 red, 0 blue, and the amount of green is going to be 1. Okay, I just spaced that out so you can see. Okay, after that, we're still doing 0 red, 0 blue, and in the middle, the next amount of green is 2, which is 1, 0. Okay, we had 0, 1. After that is 1, 0. And then the most green you could have is 3. Okay, so that's 1, 1, 0, 0. So the amount of green is the highest you can make with 2 bits, which is 1, 1. And for blue, I'll let you figure out how blue is going to go based on the pattern, but starting from 0, 0, all the way up till maximum blue. And let's keep going. And this one, same basic idea, except we're doing 9 bits per pixel and working through red, green, and blue. Okay, 9 bits per pixel means we have 3 for the red and 3 for the green and 3 for the blue, which means our range, as you can see here, is from, if we're just talking about the reds in this first row, from 0, 1, 2, 3, 4. A 4 is a 1 in the 4s column. Okay, you got to look at this as a 3-bit binary number for red, a 3-bit binary number for green, and a 3-bit binary number for blue. But of course, we're just counting up the reds and the rest is off. I think for some of you, this is going to come super easy. And some of you, I can already feel it being like lost. If you don't understand like how binary works and connects, it's going to be kind of difficult, but we'll power through. All right, so this one is kind of hard, and I'll give you 20 or 30 minutes, should be plenty to catch up through the first bubbles. So go ahead and get going. This is lesson 8 from unit 1, and we'll talk about color sampling shortly. All right, listen up for attendance. Oh, let me get Warner, is it? So go to. All right, let's go ahead and keep going or catch up or go over the next thing, whatever you want to call it. Got it here somewhere. All right, so looks like most of you got through up to where we left off, which was bubble 5, where you wanted 3 bits per color, or excuse me, 3 bits. Yes, 3 bits per color, which means 9 bits for each pixel. And here you're just going up through from 0 to 7 for the amount of red, and then the same thing, which would only be affecting the middle 3 pixels on the next row, and then only affecting the last 3 pixels on the final row. So bubble 6 and 7 are together, and I recommend opening up bubble 6 and then right-clicking and opening up 7 in another tab so that you can go back and forth quickly. And even another window is probably good also because you're going to be sort of looking at one and then the other. So from bubble 6, you can see this is your sort of first example, or this is what an App Lab output would look like. Fairly basic drop downs and images and text, and this is pretty low level stuff, pretty easy stuff. Again, low level in computer science meaning more complex. But the goal is you're going to choose one of these 4 pictures and try to create a digital version, meaning with pixels, with colors as close to you can as possible. I'm going to do this one, this image 2. I think it's probably the easiest. And then I'll take a stab at image 4. You only need to do one of them. But the key, so we'll go to image 2. You do have to hit, when you get here, you have to hit run, and then everything will update automatically. So if I think about how I would color this, I think I need at least 4 rows, because it looks like this would be one row of all the same color. This would be another row of all the same color, lighter pink. This would be another row of light yellow, and then a 4th row. So my sample size is going to be medium low, and that gives me 4 rows, and it gives me 6 columns. And so, like I said, it's probably good to have 2 windows going on. And so the width I want is 8. The height is, oh no, width is 6 for my sample right here. And the height is going to be 4. And bits per pixel. The question is how many bits per color? I think, yeah, 9 bits is fine. That'll give me 3 bits for each color. And so the way I would work through this is sort of making my palette. Okay, I need 4 different colors. And once I'm happy with those 4 colors, I'm just going to make a row out of the first color, a row out of the second color, and a row out of the third color. So my goal here is to make this top color. So let's see what happens if I do all red, no green, and all blue. That's pretty close. But I want it a little bit lighter. And the way you make any color you have lighter is by adding light to it. So raising whatever other colors that you don't want in it, raising them the same amount will make a color lighter. Okay, even though there's no green in this, if I add a little bit to the amount of green, it's gonna make it brighter. I'm adding more light. So instead of 0 for the green, let's try 2 for the green. And this isn't green at all, but having a little bit of green would make it brighter. Now, the red and blue have nowhere to go from where they are, so you can't raise the red or blue, but to make it brighter, you raise the other one. If I made it, I could make it even a little brighter with 1, 0, 0 for the green. Okay, but I need this first color, so I'm going to go 0, 1, 0. Actually, maybe even a little darker. Let's go 0, 0, 1. Okay, so that's a little bit of green, but full red and full blue. Now I need my second pink color, which is a little bit brighter, which is pretty much what I had, which is all red, a little bit of green, and all blue. In fact, I'd make it a little bit lighter, so I need a little bit more green, like that. That's probably too light. No, what did I have? 0, 0. Yep, that's pretty good for my second color. And so now I need a yellow and a light yellow. In fact, we can go ahead and make our full rows. Okay, there's a full row of that. And a full row of that. Now I need a yellow and a light yellow. I think I'm going to work with the dark yellow first, and then I'll just copy and paste and cut it around. So full yellow is red and green. So full red, full green, no blue. That's a little bright. Let's make it a little darker. The way you get the same, I want to say hue, but darker, change the brightness, is take the same amount away from all 3 channels, all 3 colors. Blue has nowhere to go farther down. So let's take a little bit away from the yellow and still have the same amount of yellow and green. That's too dark. Okay, let's go 1, 1, 0 for each color. That's still too dark. Okay, let's go back to what I had. Yeah, never mind. That's what, yeah, I guess we'll go with that for the this one, the more thorough yellow. And so I just need a sort of lighter yellow, and the lighter yellow is still going to be full red, full green, and just a little bit of blue, maybe even more blue. No, not quite that amount. Let's try that. Yep, there we go. Okay, so let's put this after this one, and do a full row of the light yellow, and then a full row of the dark yellow. That's not absolutely fantastic, but that's the basic idea. This skill of trying to figure out what the values of an RGB color are and how to change them is, I'm going to say, mildly useful at best, but it's still somewhat useful. Almost any program that has digital color interface changing, whatever, you're going to have some sort of slider or color wheel. But understanding how to make colors does, I don't know, I think it's interesting. So there's that. You can follow the same idea for the other images. So here is the thing about, I'll do a grayscale example. So image 4, it's super hard. I don't know. So for grayscale, you need to understand that all of the gray values are the same amount of red. This, guys, listen up. This is a useful concept. Just screens off, pause, pay attention. Okay. Find a view of something. Okay, listen. So, like I said, finding different brightnesses of RGB colors is interesting or useful or somewhat, but the concept that all grayscale colors are the same amount of red, green, and blue. Okay. Hey, just hang out a second. You'll have time. Relax. Guys, when I say screens off, I do mean either screens off or minimize or something. You'll have time. Relax. Okay. We know that all black is 0, 0, 0, and all white is 1, 1, 1. We have the same amount of red, green, and blue in those. Okay. If we go 6 bits per pixel, meaning we can have black would be 0 red, 0 green, 0 blue. White would be green, okay, but 1, 1 for red, 1, 1 for green, 1, 1 for blue. Another option, we have 0, 1 for red, 0, 1 for green, 0, 1 for blue, and 1, 0 for red, 1, 0 for green, 1, 0 for blue. And obviously this one would go at the end if we were doing things in order. Okay, so those are your options with 6 bits per color. At 9, well, yeah, you would only be working in 3s. Okay, 9 bits per color would be all zeros for black. Okay, going up 1 would be 0, 0, 1 for red, 0, 0, 1 for green, 0, 0, 1 for blue. Going up would be 0, 1, 0 for red, 0, 1, 0 for green, 0, 1, 0 for blue. Going up more would be 0, 1, 1 for red, 0, 1, 1 for green, 0, 1, 1 for blue, and so on. 1, 0, 0 red, 1, 0, 0 green, 1, 0, 0 blue. And I'll just do this all 101. And what comes after that? 110, 110, 110, and 111, 111, 111, even though you can't see it all. Okay, so you could start with this. If you're trying to do this grayscale image, a way to solve this is we have here a palette of 8 different grayscale shades, tones, I don't know, one of those. And if we wanted to make a 4:6 sampling where you go through each pixel, I would do it this way. I would make a 5:6 or 5:8. I don't know. Yeah, maybe 5:8. Which case we would, what is medium? Something like that. But either way, I would keep this top row as sort of my palette and go through and say, okay, this first one is like a medium darkish. So I'll take that one. And the next one is about the same. The next one goes a little bit lighter. Okay, this is just problem solving for trying to, start with a palette, in this case of all gray, and go through this and solve it that way. But you're still doing the same thing that we did with the goose picture, which is sampling, going through each pixel and choosing what color should go there. Okay. The one I showed you a second ago, the image 2, it is essentially just 4 rows of the same color. I don't know. These other ones are pretty rough. Give it a shot. I'll be impressed. But when you're done, make sure whatever you have, when you're done, you click on finish and continue to next stage so that it saves. There are, give me a second here. Let's do this. And the next bubble, let's just go over the check for understanding for a second. Actually, yeah, let's watch this brief video, which is the next bubble. And we'll go like this. Why you not go? And everything is slow today.
Hi, my name is Lamore Free, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros. Or you may have seen scary-looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only 2 options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value.
Yes, this is
There's the 1
repetitive,
position, the 10 position,
it doesn't hurt.
the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8's position, and so on. For example, the number 9 in binary is 1001. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only ones and zeros, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page or your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels.
I gotta fix that full screen thing. It's killing me here. Why? Never mind.
And each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, now we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
All right, so that wasn't too bad. Let's go like this. Nope, that's not it. Where is, all right. So the check for understandings are the only remaining two bubbles, and they are part of the assessment, assignment, activity thing. Which of these statements about analog and digital images is true? Simple, multiple choice. And the last one, describe how the process of sampling RGB pixels and binary sequences work together to display a digital color image. You know, what did we just do? Okay, so finish that up. We still have like 15 minutes left in class. 20 minutes maybe, I don't know, because of innovation. Yeah, something like that. So you have plenty of time to wrap it up. Make sure when you are done with a bubble, you hit submit or finish or continue so that it saves to that bubble and I can check it when I check the assignment. There's nothing to hand in to Canvas. I just will check your code. Okay, any questions? All right, so get to work.